Welcome to another discussion regarding the clinical laboratory. But this time, let's talk about the history and the concepts of laboratory biosafety and biosecurity. As we all know, class, the clinical laboratory contains a variety of safety hazards, many of which are capable of producing serious injury or life threatening diseases. To work safely in this environment, laboratory personnel must learn what hazard exists inside the laboratory, the basic safety precaution associated with them, and how to apply the basic rules of common sense required for everyday safety. Some hazards are unique to the healthcare environment, and others are encountered routinely throughout life. Observing and implementing laboratory safety precautions are of utmost importance in the medical technology practice. Individuals who handle and process microbiological specimens are vulnerable to pathogenic microorganisms, which are possible sources of laboratory acquired infections. Tracing back the history of laboratory biosafety and biosecurity, it actually originates from North America and Western Europe. During the year 1943, when the US are creating their biological weapons program, the practice of laboratory biosafety class was strictly administered. And this continued until the Cold War. The Cold War happened or began 1947. That's what I think. The strict adherence to laboratory biosafety was ordered by the former US President Franklin Roosevelt. But then US President Richard Nixon in 1969 terminated this US biological weapons program. Let's go back again to 1943. Ira L. Baldwin was the first scientific director of Camp Detrick, which eventually became Fort Detrick. He was tasked with establishing the biological weapons program for defensive purposes to enable the United States to respond if ever there will be attack by such weapons. Camp Detrick became the primary or permanent installation for biological research and development after the World War II. Kindly write this down. Newell A. Johnson, he designed modifications for biosafety at Fort Detrick. He engaged some of Camp Detrick's leading scientists about the nature of their work and developed specific technical solutions such as Class 3 safety cabinets and laminar flow hoods to address specific risks. Their consequent meetings became a formation of the American Biological Safety Association in 1984. And soon, class, they did this annually. Arnold Vedum was not from the United States, but also he contributed to the basic concepts of lab biosafety. He described the use of mechanical pipeters to prevent laboratory acquired infections in 1907 and 1908. For me, this is considered to be a breakthrough also in the practice of medical technology since medtechs before or scientists before used to mouth pipette samples, so body fluids that can be either urine or any other body fluids that are collected from the patient are mouth pipetted by laboratory scientists. Ventilated cabinets, early progenitors to the nearly ubiquitous engineered control, now known as the biological safety cabinet, were also first documented outside the United States Biological Weapons Program. Also, in the year 1909, a pharmaceutical company in Pennsylvania developed a ventilated cabinet to prevent infection from Mycobacterium tuberculosis. This is the causative agent for what disease? What do you think? It's tuberculosis. It was also during the time of the smallpox pandemic in 1967 where there was increasing mortality and morbidity rate. The World Health Organization class aggressively pursued the eradication of the virus. How do you think they completely eradicated this virus? It is through vaccination. So I hope, class, that in this time of the COVID 19 pandemic, you will have the courage and you will all be ready to take in the shot. However, it is still your freedom to choose whether you take in the vaccination or not. So when the time is right and you'd be ready, you may take the vaccination. Okay? Let's go back to the smallpox era. It was also during this time that serious concerns regarding laboratory biosafety practices worldwide were raised, and they were contributing directly to the decision of the World Health Assembly to consolidate the remaining virus stocks into two locations: just the Center for Disease Control and Prevention in the United States and the State Research Center of Virology and Biotechnology, otherwise known as Vector, in Russia. I want also to emphasize in my lecture that in the year 1974 class, the Centers for Disease Control and Prevention published the classification of etiological agents on the basis of hazard that introduced the concept of establishing ascending levels of containment associated with risks in handling groups of infectious microorganisms that present similar characteristics. 2 years later, that means 1976, the National Institutes of Health of the United States published the NIH guidelines for research involving recombinant DNA molecules. It was explained in great detail the microbiological practice, equipment, and facility necessarily corresponding to the four ascending levels of physical containment. The guidelines that are published laid the very foundation for the introduction of a code of biosafety practice. This code, along with the World Health Organization's first edition of Laboratory Biosafety Manual that was produced last 1983, and the Centers for Disease Control and Prevention and National Institutes of Health jointly published first edition of the Biosafety in Microbiological and Biomedical Laboratories. That was also in 1984. These mark the development of the practice of laboratory biosafety. If you wish to read more regarding the classification of etiological agents on the basis of hazard and also the NIH guidelines for research involving recombinant or synthetic nucleic acid molecules, I will be providing the websites that you may read to feed also your curiosity. However, I will not be including that in my examination. So kindly read in the description part of my video. I will be providing the website or the web page for that. This progress in biosafety practice continued until the emergence of a community of biosafety officers who adopted the administrative role of ensuring that the proper equipment and facility controls are in place based on the specified biosafety level of the laboratory. Arnold Vedum, the Director of Industrial Health and Safety at the U.S. Army Biological Research Laboratories in 1944, was recognized as one of the pioneers of biosafety that provided the foundation for evaluating the risks of handling infectious microorganisms and for recognizing biological hazards and developing practices, equipment, and facility safeguards for their control. In 1966, Vidom and another microbiologist, Morton Reitman, colleagues at Fort Detrick analyzed multiple epidemiological studies of laboratory based outbreaks. Let's now proceed to the brief history of laboratory biosecurity. In the year 1996, the US government enacted the Select Agent Regulations. This is to monitor the transfer of a select list of biological agents from one facility to another. Slightly after the terrorist attacks and the anthrax attacks of 2001, also known as Amerithrax, the US government changed its perspective. The revised Select Agent Regulations then required specific security measures for any facility in the United States that used or stored one or more agents on the new, longer list of agents. Just to give you a brief background regarding the anthrax attacks in the United States, this actually took place 1 week after the 9/11 terrorist attacks of the Twin Towers. So specifically, that happened September 18 when letters containing the bacterial spores of anthrax were mailed to several news media offices and also to Democratic Senators Tom Daschle and Patrick Leahy, killing 5 people and infecting 17 others. Mode of transmission, so that one can get infected with the anthrax bacilli, is through inhaling the bacterial spores. By then, the anthrax attacks or the anthrax bacilli itself became a biological weapon for terrorists. You will get to know more about the anthrax bacilli in your microbiology class in the third years. The revision of the Select Agent Regulations in 2012 sought to address the creation of two tiers of select agents. Tier 1 agents are materials that pose the greatest risk of deliberate misuse, and the remaining select agents. Kindly familiarize some Tier 1 select agents, and you will also learn more about them in microbiology class. The revisions that were made was intended to make the regulations more risk-based, mandating additional security measures for Tier 1 agents. Other countries also relatively implemented and prescribed biosecurity regulations for bioscience facilities. Singapore's Biological Agents and Toxins Act is similar in scope with the US regulations, but with more severe penalties for non-compliance. In South Korea, the Act on Prevention of Infectious Diseases in 2005 was amended to require institutions that work with listed highly dangerous pathogens to implement laboratory biosafety and biosecurity requirements to prevent the loss, theft, diversion, release, or misuse of these agents. In Japan, the Infectious Disease Control Law was recently amended under Japan's Ministry of Health, Labor, and Welfare. It also established 4 schedules of select agents that are subject to different reporting and handling requirements for possession, transport, and other activities. Then in Canada, Canadian Containment Level 3 and 4 facilities that work with risk group 3 or 4 are required to undergo certification. In 2008, the Danish Parliament passed a law that gives the Minister of Health and Prevention the authority to regulate the possession, manufacture, use, storage, sale, purchase, or other transfer, distribution, transport, and disposal of listed biological agents. Around the world class, biosecurity implementation has become a purely administrative activity based on a government developed checklist. Let us list down all the local and international guidelines regarding laboratory biosafety and biosecurity. In Feb 2008, the Comité Européen de Normalisation, this is a European Committee for Standardization, published the CEN Workshop Agreement 15793. This focuses on laboratory biorisk management. The workshop offers a mechanism where stakeholders can develop consensus standards and requirements in an open process. The CWE 15793 can be applied to international stakeholders. However, they do not have the force of regulation while conformity is voluntary. The CWA 15793 was developed among experts from 24 different countries, including Argentina, Australia, Belgium, Canada, China, Denmark, Germany, Ghana, UK, US, and among others. It was updated in 2011 and intended to maintain a biorisk management system among diverse organizations and set out performance-based requirements with the exclusion of guidance for implementing a national biosafety system. This agreement was used until it officially expired in 2014. In order to address concerns on biosafety guidance for research and health laboratories, the issues on risk assessment and guidance to commission and certify laboratories, the World Health Organization in 1983 published its third edition of the Laboratory Biosafety Manual. It includes information on the different levels of containment laboratories from BSL 1 to 4. There are also different types of biological safety cabinets that we will be discussing later on, the good microbiological techniques, and how to disinfect and sterilize equipment. In terms of biosecurity, it covers the packaging required by international transport regulations and other types of safety procedures for chemical, electrical, ionizing radiation, and fire hazards. The manual puts emphasis on the continuous monitoring and improvement directed by a biosafety officer and a biosafety committee. However, there is no mechanism to ensure that the WHO biosafety guidance is being adhered to or that people working in laboratories are sufficiently trained. The Cartagena Protocol on Biosafety, made effective in 2003, which applies to the 168 member countries, provides an international regulatory framework to ensure an adequate level of protection in the field of safe transfer, handling, and use of living modified organisms resulting from modern biotechnology. The regulations primarily tackle the safe transfer, handling, and use of LMOs that may have adverse effects on the conservation of biological diversity, except those that are used for pharmaceuticals purposes. In addition, the legislation provides a framework for assessing the risk of LMOs and is focused on ensuring that LMOs do not negatively affect biodiversity. Please read the Articles 8 and 19 of the Cartagena Biosafety Protocol. You may also take a screenshot of this so that you can proceed to the next slide. The new National Committee on Biosafety of the Philippines, or the NCBP, established under the Executive Order 430, Series of 1990, was formed on the advocacy efforts of scientists. The mandate of NCBP focuses on the organizational structure for biosafety, procedures for evaluation of proposals with biosafety concerns, procedures and guidelines on the introduction, movement, and field release of regulated materials, and procedures on physico chemical and biological containment. On March 17, 2006, the Office of the President promulgated Executive Order 514, establishing the National Biosafety Framework. This one prescribes the guidelines for its implementation, strengthening the National Committee on Biosafety of the Philippines. The National Biosafety Framework is a combination of policy, legal, administrative, and technical instruments developed to attain the objective of the Cartagena Protocol on Biosafety, which the Philippines signed on May 24, 2000. The NBF can be considered as an expansion of the NCBP, which since 1987 has played an important role in pioneering the establishment and development of the current biosafety system of the country and was acknowledged as a model system for developing countries. The Department of Agriculture also issued Administrative Order Number 8 to set in place policies on the importation and release of plants and plant products derived from modern biotechnology. The Department of Health, together with NCBP, formulated guidelines in the assessment of the impacts on health posed by modern biotechnology and its applications. The guidelines aid in evaluating and monitoring processed food derived from or containing GMO. Currently, DOH, in the midst of technological advances, recognizes the need to update the minimum standards and technical requirements for clinical laboratories. It requires clinical laboratories to ensure policy guidelines on laboratory biosafety and biosecurity based from the Department of Health's Administrative Order Number 2007-0027. Let us also discuss the different organizations in the field of biosafety. As we all know, there are already several organizations across the entire world that has undertaken initiatives in advocating for laboratory biosafety and biosecurity. The following organizations that I am going to show you are some prominent organizations inside and outside the Philippines. Number one, we have American Biological Safety Association. Ebsa was founded in 1984 to promote biological safety as an essential principle and serve the needs of biosafety professionals. The association's goals are to represent the interests and desires of practitioners of biosafety and to be a dispenser of biosafety information. The concept of biological safety or biosafety has paralleled the development of the science of microbiology and its extension into new and related areas including tissue culture, recombinant DNA, animal studies, molecular biology, synthetic biology, and biotechnology. The knowledge and skills gained by microbiologists necessary to isolate, manipulate, and propagate pathogenic microorganisms required parallel development of containment principles, facility design, and practices and procedures to prevent occupational infections in the workplace or release of the organisms to the environment. The next one is Asia Pacific Biosafety Association, or the APBA. This organization started on February 22, 2005, and is representing over 800 practicing biosafety professionals from more than 40 nations around the Asia Pacific region and outside the region, namely Afghanistan, Australia, Bangladesh, Belgium, Germany, Hong Kong, India, Indonesia, Ivory Coast, Japan, Netherlands, New Zealand, Pakistan, and many more. This professional association is for biological safety for the promotion of biosafety and biosecurity information through biosafety and biosecurity trainings and conferences in the region, the formation of the national biosafety with national, regional, and international collaborations and partnerships with various stakeholders. Other members include Singapore, Brunei, China, Indonesia, Malaysia, Thailand, Philippines, and Myanmar. Their mission is to advance biological safety and security with sustainable practices in the Asia Pacific region. And their main goal is to provide a professional forum that represents the regional interests and biological safety practitioners and to provide a platform promoting constructive with the scientific community, governments, civil society, and the private sector. The objectives of APBA are to upgrade acknowledgement and underwriting of APBA as dependable and equipped executing accomplice in fortifying biosafety and biosecurity measures and best practices. They also want to advance and create national biosafety associations and country biosafety working groups and to completely incorporate all of these. They also want to promote biosafety and biocontainment innovation as a solid calling and upgrade acknowledgement that the individuals who work with organic materials ought to be talented and capable in biosafety models and best practices. APBA also ought to instruct key administrative, political, open, and private partners on the need to reinforce manageable biosafety practices and research facility base or gear utilizing down to earth hazard based arrangements that can be worked and kept up in a protected and secure way utilizing neighborhood assets. Another objective of APBA is also to target key universal general well-being activities to guarantee they incorporate biosafety and biosecurity needs, assets, and motivation for activity that improve feasible biosafety limit among therapeutic research center professionals and researchers. The third organization that is found in the book is the European Biological Safety Association or the EBSA. EBSA is a non-profit organization founded in June 1996, which provides a forum to its members to discuss and debate issues of concern and to represent those working in the field of biosafety and associated activities. Its mission is to enhance knowledge and understanding of biological safety throughout Europe and the world. EBSA also focuses on encouraging and communicating among its members information and issues on biosafety and biosecurity, as well as emerging legislation and standards. Next one is an organization found in the Philippines, the Philippine Biosafety and Biosecurity Association. PHBBA was brought about by a multidisciplinary team including members from healthcare, academia, emergency response, pharmaceutical or biotech, in addition from the executive, legislative, and judicial branches of the government. The membership of PHBBA also comprised members of the steering committee and technical working groups of the National Laboratory Safety Action Plan Task Force, which created as per DPO number 2006-2500, dated September 15, 2006. A long-term goal of the association is to help the Department of Health and Agriculture in their efforts to create a national policy and implementation plan for laboratory staff and biosecurity. Another organization that is also found in the Philippines is the Biorisk Asiation of the Philippines 2015 Incorporated. This is a non-government and non-profit association wherein its officers and members work to serve the emergent concerns of biological risk management in various professional, medical, agricultural, technological, and biological sectors throughout the Philippines. BRAP cooperates and collaborates with other associations, more specifically with Biosafety and Biosecurity, technology, research, private and public health or technology organizations, corporate or private, throughout the Philippines and globally in the promotion of biosafety, biosecurity, and biorisk management as scientific disciplines. BRAP goes by the tagline Assess, Mitigate, and Monitor. The World Health Organization issued a common understanding of biosafety derived from the practical guidance on techniques to be used in laboratories. Biosafety has long been practiced in most nations, especially among institutions that handle and process microbiological specimens. The WHO Laboratory Biosafety Manual defines biosafety as the containment principles, technologies, and practices that are implemented to prevent unintentional exposure to pathogens and toxins or their accidental release. In simpler terms, class, biosafety means the application of knowledge, techniques, and equipment to prevent personal, laboratory, and environmental exposure to potentially infectious agents or biohazard. Biosafety is defined as the containment conditions under which these infectious agents can be safely manipulated. Because the main objective of containment is to confine all these biohazards and to reduce the potential exposure of the laboratory worker, that includes you, the persons outside of the laboratory, that may be your family or your friends, and the environment where you live, to potentially infectious agents. While the term biosecurity means the protection, control, and accountability for valuable biological materials within laboratories in order to prevent their unauthorized access, loss, theft, misuse, diversion, or intentional release. Let us define it again in simpler terms so that it will sound easy for you, class. Biosecurity refers to the measures aimed at preventing the introduction or spread of harmful organisms like viruses, bacteria, even parasites, and fungus or fungi. So we prevent them from spreading and hurting animals and plants in order to minimize the risk of transmission of infectious diseases. When we place it in an agricultural aspect, these measures are aimed at protecting our food crops and livestock from pests or invasive species and other organisms not conducive to the welfare of the human population. The term biosecurity also includes biological threats to people, including those from pandemic diseases and bioterrorism, like the anthrax that I have mentioned prior to this discussion. The definition has sometimes been broadened to embrace other concepts, and it is used for different purposes in different contexts. Let's say, for example, the COVID-19 pandemic is a threat for which biosecurity measures have been needed in all countries of the world. So that you will have a better understanding and easier comprehension regarding the terms, let's state it in key terms, okay? So when we say biosafety, it means protecting the people against the germs. While for biosecurity class, you protect the germs from the people. To sum it all up, biosafety focuses on laboratory procedures and practices necessary to prevent exposure to and acquisition of infections, while the maintenance of secure procedures and practices in handling biological materials and sensitive information falls under biosecurity. Biosafety and biosecurity share common perspectives in terms of risk assessment and management methodologies, personnel expertise and responsibility, control and accountability for research materials, including microorganisms and culture stocks, access control elements, material transfer documentation, training, emergency planning, and program management, among others. It was actually Charles Baldwin, an environmental health engineer working for the Dow Chemical Company. He created the biohazard symbol used in labeling biological materials carrying significant health risk. That was in the year 1966. Let's now proceed to the classifications of microorganisms according to risk groups. The World Health Organization recommends an agent risk group classification for laboratory use that describes 4 general risk groups based on principal characteristics and relative hazards posed by infectious toxins or agents. The risk group classification for humans and animals is based on the agent's pathogenicity, mode of transmission, host range, and the availability of preventative measures and effective treatment. Risk groups are classifications that describe the relative hazard posed by infectious agents or toxins in the laboratory. The risk group to which an infectious agent or toxin is assigned is a primary but not only consideration used in a biological risk assessment to determine the appropriate biosafety level in which a worker can handle the infectious agent or toxin. Just a reminder, risk group levels do not always correspond to biosafety levels. Let's say, for example, a specific research project's biological risk assessment for the use of human immunodeficiency virus or the HIV. A risk group 3 agent may correctly determine that HIV can be handled safely under biosafety level 2 conditions. Risk groups are designated from 1, which is the lowest risk, to 4, considered to be the highest risk. You may take a screenshot of this so that we can proceed to the next slide. When we say risk group 1, this includes microorganisms that are unlikely to cause human or animal disease. These microorganisms bring about low individual and low community risk. Risk group 2 includes microorganisms that are associated with human diseases but is rarely serious and for which preventive or therapeutic interventions are often available. These agents represent a moderate risk to an individual but a low risk to the community. Using this photo from IGEM, risk group 1's typical work area can be done on an open bench, meaning on your working table in the laboratory. An example of this group are Escherichia coli K12, S. cerevisiae or the yeast, can also have the lactobacillus or the Bacillus subtilis species. While the working area for risk group 2 microorganisms makes use of a biosafety cabinet. An example of a risk group 2 microorganism is Streptococcus, the bacteria responsible for the strep throat. This bacteria class, if left untreated, can cause very deleterious effects to the body. It can affect the heart or the kidneys. Risk group 3 includes microorganisms that are known to cause serious diseases to humans or animals and may present a significant risk to laboratory workers. It could present a limited to moderate risk if these microorganisms spread in the community or the environment, but there are usually effective preventive measures or treatment available. They bring about high individual risk and limited to moderate community risk. While lastly, for risk group 4 microorganisms, they are known to produce life-threatening diseases to humans or animals. It represents a significant risk to laboratory workers and may be readily transmissible from one individual to another, while effective treatment and preventive measures are not usually available. In effect, they bring about high individual and high community risk. Let's use again this photo from IGEM, the comparison between risk group 3 and risk group 4. As what you can see there, the typical PPEs or personal protective equipment per risk group differs also, while the working area for risk group 3 makes use of a class 3 biosafety cabinet, while for risk group 4 makes use of full isolation suits. The examples of microorganism under risk group 3 includes Yersinia pestis, which is responsible for Black Plague, the human immunodeficiency virus, and even the severe acute respiratory syndrome virus or the SARS virus. While for risk group 4 microorganisms, usually it involves viruses. So Ebola, Marburg, and Lassa viruses. All of these doesn't have treatment yet nor vaccination available. So it is expected that the microorganisms under risk group 4 are very deadly and dangerous. Aside from the risk groups, we must also learn the categories of laboratory biosafety according to their levels. In order to facilitate precautionary measures, Centers for Disease Control and Prevention categorize laboratories into 4 biosafety levels. Biosafety level designations are based on a composite of the design features, construction, containment facilities, equipment, practices, and operational procedures required for working with agents from the various risk groups. They are designated still in ascending order by degree of protection provided to the personnel, the environment, and the community. When we say Biosafety Level 1, this is suitable for work involving viable microorganisms that are defined and with well-characterized strains known not to cause diseases in humans. Examples of microorganisms being handled in this level are Bacillus subtilis, Naegleria groberi, infectious canine hepatitis virus, and exempt organisms under the NIH guidelines. This level is the most appropriate among undergraduate and secondary educational training and teaching laboratories that require basic laboratory safety practices, safety equipment, and facility design that requires basic level of containment. The next type of biosafety level is Biosafety Level 2. This is basically designed for laboratories that deal with indigenous moderate risk agents present in the community. It observes practices, equipment, and facility design that are applicable to clinical, diagnostic, and teaching laboratories, consequently observing good microbiological techniques. Examples of microorganisms that could be handled under this level are hepatitis B virus, HIV, Salmonella, and Toxoplasma species. BSL2 is appropriate when work is done with human blood, body fluids, tissues, or primary human cell lines where there is uncertain presence of infectious agents. Hand washing sinks and waste decontamination facilities must be available, and access to the laboratory must be restricted when work is being conducted. All procedures where infectious aerosols or splashes may be created are conducted in biosafety cabinets or other physical containment equipment. Biosafety Level 3 puts emphasis on primary and secondary barriers in the protection of the personnel, the community, and the environment from infectious aerosol exposure. Work with indigenous or exotic agents with the potential for respiratory transmission and that may cause serious and potentially lethal infection are being conducted here. Examples of microorganisms handled here are Mycobacterium tuberculosis, St. Louis encephalitis virus, and Coxiella. All laboratory activities are required to be performed in a biosafety cabinet or other containment equipment like a gas-tight aerosol generation chamber. Secondary barriers for this level are highly required, including controlled access to the laboratory and ventilation requirements to minimize the release of infectious aerosols from the laboratory, while special engineering and design features are also being considered. Personnel must be supervised by scientists competent in handling infectious agents and associated procedures in a BSL-3 laboratory. Lastly, we have Biosafety Level 4. This is required for work with dangerous and exotic agents that pose high individual risks of life-threatening diseases that may be transmitted via the aerosol route, for which there are no available vaccines or treatment. Specific practices, safety equipment, and appropriate facility design and construction are required, for instance, when manipulating viruses such as the Marburg or Crimean Congo hemorrhagic fever, and any other agents known to pose a high risk of exposure and infection to laboratory personnel, community, and environment. The laboratory workers' complete isolation from aerosolized infectious materials is accomplished primarily by working in a Class 3 biosafety cabinet or in a full-body, air-supplied positive pressure personnel suit. A BSL-4 laboratory is generally a separate building or completely isolated zone with specialized ventilation requirements and waste management systems. Laboratory staff must have specific and thorough training in handling extremely hazardous infectious agents. The laboratory is controlled by the laboratory supervisor in accordance with institutional policies. The next video is a video created by the National Institutes of Health, which shows what a biological safety cabinet looks like, how to use it, what are the mechanisms of this instrument, and the guidelines in order to use them properly.
This video demonstrates how biological safety cabinets work to protect you, providing protection to laboratory workers, product, and the environment while reducing the risk of exposure. Thoroughly understanding how a biological safety cabinet works while following established lab safety protocols will help prevent contamination of your work and protect you at the same time. When used correctly, a properly installed and certified biological safety cabinet provides personnel, environmental, and product protection for work with biological materials, including infectious agents and recombinant DNA. This video depicts a freestanding Class 2 Type A2 biological safety cabinet, or BSC. It includes HEPA filters for exhaust and supply air, the work surface, the opening to the work surface, the airfoil, front and rear air intake grills, the plenum. The BSC's air filtration system works to keep potentially contaminated air from seeping back onto the worker. Air flows through the window opening into the front grille, through the plenum, then through the HEPA filters. 30% of the filtered air is exhausted. The remaining 70%, which is now HEPA filtered, is recycled back into the workspace. To ensure maximum protection in using a BSC, here are some essential reminders. 1. If the cabinet has been turned off, you must turn it on and wait at least 15 minutes before beginning your work. 2. Set up the interior workspace to work from clean to dirty, and work consistently from one direction toward the other to prevent cross-contamination. 3. Place your chair at a comfortable height and in the middle of your workspace to ensure you can reach everything you need inside the cabinet without discomfort. Please keep in mind that you must work at least 10 centimeters inside the BSC. To guarantee uninterrupted airflow, cabinets should never be overcrowded. Overcrowding the BSC can block air grills. Airflow can also be disrupted by sudden or sweeping movements. Slow, direct movements work best. Too much foot traffic can cause problems as well, and should be kept at a minimum. If pedestrians are unavoidable, keep people at least 1 meter from your BSC. And remember to check nearby doors or supply vents to determine if they disrupt the cabinet's airflow. When you have completed your work, any reusable items should be wiped down with disinfectant before removing them from the BSC. Next, the interior surfaces of the BSC should be decontaminated using the appropriate disinfectant for a contact time recommended for the agent used. To be sure, a second decontamination is advisable. In summary, there are a small number of best practices to follow in using a biological safety cabinet. Let's go over them one last time. Work at least 10 centimeters inside of the BSC. Do not block front and rear grills. Too many objects in the BSC can disrupt the airflow. Set up workspace in a direction from clean to dirty. Use slow, direct movements. Minimize foot traffic within 1 meter of the BSC. Placement of the BSC away from doors and room air supply vents helps maintain airflow.
The next video will show you what a biosafety level 4 laboratory looks like. And I got this video from CSIRO.
CSIRO's Australian Animal Health Laboratory, known as AL, is a frontline defence, helping to protect Australia from the threat of exotic and emerging animal diseases. This national facility has developed a significant international reputation as one of the world's finest animal bioscience research laboratories. And it's the most sophisticated laboratory in the world for the safe handling and containment of infectious microorganisms. Opened in Geelong, Victoria in 1985, the laboratory was the most technically complex of its time. AL's reputation for engineering excellence continues today, with the recent implementation of award-winning contemporary automation and control system technologies. Research is undertaken here to develop new diagnostic tests and other decision support tools for limiting disease spread, and for the creation of new vaccines and treatments to protect animals and humans from disease. The threat that infectious diseases pose to human, animal and environmental health is a global concern. In the last 20 years, some 30 new and highly infectious diseases have been identified, including Hendra virus, SARS, Ebola and HIV/AIDS. Many of these diseases don't have a cure. Collaborative Biosecurity Research Facility, known as the ACBRF. It's the most advanced facility of its kind in the world, and provides Australia with a unique opportunity to lead biosecurity research globally. As well as undertaking the identification and characterisation of viruses, this new facility will be used to investigate the origin, development and treatment of animal and zoonotic diseases, or diseases that are harmful to both people and animals. Before entering the laboratory, scientists pressurize the fully encapsulating positive pressure suit, the latest model available to scientists, and check both air supplies to ensure their equipment and lifelines are operating efficiently. Once inside, they can then move around freely. The ACBRF provides scientific staff with an opportunity to work with small laboratory animals, including insects, inside 3 spacious animal rooms. There's also an ante-room for equipment, including freezers and centrifuges, and a large general laboratory. This general laboratory is unique, as it allows up to 12 scientists to work at any one time within the specialised space on research of national importance at the highest level of biosecurity. It has 5 independent workstations and features state-of-the-art equipment, including Class 2 biological safety cabinets and incubators. The ACBRF also incorporates the et.al. Biosecurity Microscopy Facility, a specialist microscopy service that enables fundamental research with infectious disease agents that require the highest levels of containment. The control room overlooks the imaging facility where scientists can communicate with staff and remotely control the microscope.
One area that excites microscopes to record the virus attaching to the cell, entering the cell, replicating and leaving the cell. In addition, we'll be able to look at the impact of the virus on the cell and transmit those images in real time to researchers here at et.al. within Australia and overseas.
Although the laboratory is in the heart of et.al.'s secure area, staff aren't isolated from other parts of the facility or the outside world. They can communicate with each other, make contact with the central monitoring officers, as well as with scientists outside the laboratory at any time. All activities within the facility are under 24-hour closed-circuit TV surveillance. This footage can be viewed over a secure web connection and interfaced into a new communication system called the Biosecurity Collaboration Platform. et.al.'s original suit room will be used as a secondary work area when the large PC4 laboratory is decontaminated and shut down for maintenance. This is a mandatory requirement and will occur on an annual basis. In building this laboratory, the CSIRO has worked and continues to work closely with regulators to ensure the new facility meets all the current requirements set by the Australian Government's Office of the Gene Technology Regulator and the Australian Quarantine and Inspection Service, all done as part of the CSIRO's commitment to operating a safe and secure laboratory. The ACBRF complements existing facilities within et.al.'s biocontainment area. For example, the large animal facility is the most sophisticated, microbiologically secure research facility of its kind in the world. It provides the CSIRO with the ability and flexibility to work with any animal species and pathogens at the highest level of biosecurity. The ACBRF also offers a specialised training facility to help scientists gain experience and confidence working in conditions that mimic a PC4 environment. This facility is designed to avoid the distractions, delays, and most importantly, the risks associated with training in an active workspace. Everything within the ACBRF is treated before it leaves. The air is filtered, all sewage is heat-treated, and solid waste is incinerated. As part of this biocontainment procedure, all staff leaving the laboratory must complete a 7-minute chemical wash before removing and leaving behind their suit and laboratory clothes. They must then shower out through an airlock. The shower process is then repeated in order to exit the secure area. Once outside the laboratory, staff must not have contact with livestock animals for 7 days. In the past 2 decades, the CSIRO has been at the forefront of the discovery and control of several significant emerging infectious diseases, including equine influenza, Hendra virus, and SARS. The laboratory continues to be a partner in numerous research collaborations, both nationally and internationally. The CSIRO welcomes and encourages the international research community to work within the ACBRF on a marginal cost recovery basis to undertake projects of global importance.
This facility can make a real difference to Australian biosecurity.
In the laboratory, we also have hazardous materials classification. 1 is colored yellow and labeled instability. 2 is colored red for fire hazard. 3 is colored blue for health hazard, while the use no water sign is colored white, which indicates specific hazards. So I want you all to memorize and familiarize this diagram, as well as the scoring. Lastly, before we end our discussion, I want to introduce to you the Occupational Safety and Health Administration. This is a large regulatory agency of the United States Department of Labor that originally had federal visitorial powers to inspect and examine workplaces. Their main mission is to assure safe and healthy working conditions for working men and women by setting and enforcing standards and by providing training, outreach, education, and assistance. The agency is also charged with enforcing a variety of whistleblower statutes and regulations. Occupational Safety and Health Administration's workplace safety inspections have been shown to reduce injury rates and injury costs without adverse effects to employment, sales, credit ratings, or firm survival. The Congress established this agency under the Occupational Safety and Health Act, which President Richard M. Nixon signed into law on December 29, 1970. For those who want to read more regarding the classification of infectious microorganism by risk group, this one shows a very good comparison between the NIH guidelines and the World Health Organization Laboratory Biosafety Manual. This one is also showing you the summary of recommended biosafety levels for infectious agents. The main source for this is the United States Department of Health and Human Services 2019. The title of the book is Biosafety in Microbiological and Biomedical Laboratories. Thank you so much for listening to this very long discussion. I hope you got interested in learning more regarding the basic concepts of laboratory biosafety and biosecurity. Please keep safe and continue to follow minimum health protocols set by our government. God bless you always and have a great day.